For a long time, we've treated two of our greatest scientific achievements like they live in different neighborhoods. In one corner we have general relativity, Einstein's grand theory of the very big, stars, galaxies, the graceful curve of space-time. In the other, we have quantum mechanics, the strange and wonderful rules that govern the very small, atoms, electrons, and the fizzing energy of the void. We've always been told these two theories don't talk to each other. They use different languages, different math. But what if that separation is our own misunderstanding? What if the universe doesn't see a divide at all? The cosmos, in its immense wisdom, might be using the same rulebook for everything. Imagine trying to understand an ocean by only studying a single drop of water, or by only looking at the massive waves. You'd get two very different pictures and they might seem contradictory, yet they are both parts of the same single entity. The universe could be just like that. The laws that make a star collapse and the laws that make an atom vibrate could be two sides of the same cosmic coin. The search for a theory of quantum gravity is precisely this: the quest for a unified description that shows us how the tiny quantum world builds the grand stage of the cosmos we see above us. This quest challenges us to think differently. Instead of trying to force the rules of the big onto the small or vice versa, perhaps we need to step back and find the common ground where they both emerge. The universe is not schizophrenic. It doesn't use one set of laws for planets and another for photons. The separation we perceive is a limit of our perspective, not a feature of reality. We are standing at a threshold, ready to peer over the fence we built ourselves and see that the two fields were never truly separate. They were always connected, waiting for us to find the key. This journey begins by questioning our most fundamental assumptions. We look at the cosmos through our human-made lenses, with concepts we invented to make sense of our world. But the universe doesn't have to play by our rules, or fit into our neat little boxes. To find the secret code, we must be willing to let go of what we think we know. We must be prepared to discover that the most extreme objects in the cosmos, the places where gravity is strongest and matter is densest, are where the two sides of this story finally come together in a spectacular universe-shaping dance. Black holes have a fearsome reputation. We picture them as cosmic monsters, ravenously swallowing everything that dares to venture too close. Stars, planets, even light itself. They are the ultimate cosmic dead end, a point of no return where information and matter are lost forever. But is that the whole story? What if this popular image is fundamentally wrong? What if black holes are not destroyers but cosmic negotiators? Imagine them not as graveyards but as cosmic reset buttons, places where the universe gets a chance to start over, to rearrange its fundamental structure in the most profound way possible. Instead of annihilating matter, perhaps a black hole's immense gravity forces it into its most basic form, a pure quantum state. Think of it like taking a complex Lego castle and breaking it down into its individual bricks. The castle is gone, but all the pieces are still there, ready to be rebuilt into something new. In this view, a black hole is a crucible, a place where the familiar rules of space and matter are melted down. It doesn't erase the universe's building blocks, it just returns them to the quantum drawing board, ready for a new creation. The matter and energy that fall in are not destroyed, but transformed. This idea offers a beautiful solution to a nagging cosmic puzzle, the second law of thermodynamics, which says that entropy, or disorder, always increases. If the universe is constantly getting messier, how did it start in such an orderly state? Black holes could be the answer. By taking in chaotic, disorganized matter and collapsing it into a highly structured, unified quantum state, they could be seen as entropy-reducing engines. They are not contributing to the universe's messiness, they are tidying up, one star at a time. They are the universe's natural recyclers, turning cosmic clutter back into pristine potential. So, these cosmic behemoths might not be the villains of our cosmic story. They might be the architects. They could be the mechanism by which the universe balances its own books, ensuring that a state of pure potential is always preserved. They are the bridge between the large-scale world of gravity and the small-scale world of quantum mechanics, the very places where the universe reveals its unified nature. When we look at a black hole, we might not be staring into an abyss of nothingness, but into the heart of creation itself, a place of ultimate renewal. What is time? We live by it. Our clocks, calendars, and schedules dictate our lives. We feel it passing moment by moment. It seems so real, so fundamental. But what if time, as we know it, is not a fundamental feature of the universe? What if it's a human invention, a concept we created to measure the sequence of events in our own experience? The cosmos itself might not operate on a schedule. The universe simply is. We are the ones who slice its existence into past, present, and future. It's a powerful tool for us, but it may just be a story we tell ourselves. Consider a simple everyday example. If you get on a plane in New York and fly to London, you lose 5 hours. Did you travel into the future? Of course not. You simply moved from one human-defined time zone to another. Your watch changed, but the universe didn't skip a beat. Time, in this sense, is a local agreement, a convention. The idea of a single universal, now that everyone experiences simultaneously, is an illusion. Einstein's theory of relativity showed us this with time dilation. The faster you move, the slower time appears to pass for you relative to a stationary observer. But maybe it's not time that's stretching or shrinking. Perhaps what we call time dilation is just a way of describing how matter and energy interact differently at different speeds. The universe doesn't have a master clock. There is only cause and effect, a chain of interactions happening at the quantum level. We perceive these interactions as a flow, a sequence, and we call that perception time. But the fundamental reality might just be a vast web of relationships, where everything influences everything else without the need for a ticking clock in the background. Things change, but that change doesn't require a dimension called time to happen in. When we look out at the cosmos, we see evidence of this. The cosmic microwave background radiation, the faint afterglow of the Big Bang, is often described as a snapshot from 380,000 years after the beginning. But what if it's just a measure of distance and energy state? The Hubble constant, which describes the universe's expansion, is measured in kilometers per second per megaparsec, a rate of change, not a clock speed. Removing the abstract concept of time from these observations doesn't break them. In fact, it might make them clearer, revealing a universe governed not by a temporal timeline but by the timeless laws of physics. If a black hole is a place where everything goes in and nothing comes out, what would its opposite be? Logically, it would be a place where everything comes out and nothing goes in. This theoretical cosmic object is called a white hole. For a long time, white holes were considered a mathematical curiosity, a solution to Einstein's equations that probably didn't exist in reality. But what if we've already seen the effects of the most spectacular white hole of them all? What if our own Big Bang was, in fact, a white hole event? Imagine all the matter and energy of our universe compressed into an impossibly small, dense point, a singularity. This is the state a black hole creates. Now what if that singularity, having reached a state of pure quantum order, bounced? Instead of staying a black hole forever, it emerges, spewing forth all its contents in a tremendous outpouring of energy and matter. This is exactly what we think happened at the start of our universe. The Big Bang wasn't an explosion space, it was an explosion space, an emergence of everything we see from a single point. A white hole provides a perfect model for this event. Let's construct a simple model for how this could happen. In the beginning, there was just a sea of fundamental particles. Through random collisions, some of these particles clumped together, their collective gravity pulling in more and more until a massive black hole formed. This black hole continued to grow, swallowing matter until it contained the potential for an entire universe. Once it reached a critical density, the quantum state inside could no longer be contained. It rebounded, reversing its collapse and becoming a white hole. Our universe was born from this incredible cosmic reversal. This model also helps explain a curious observation. It seems our Milky Way galaxy resides in a large, relatively empty area of space called a cosmic void. Why would that be? If our universe emerged from a white hole, the initial expansion would have been incredibly rapid and turbulent. Some regions would have shot out faster, leaving others behind. Our galaxy and our local group of galaxies might simply be catching up to the outer edge of the expansion. We are not in a void because we are isolated, but because we are part of a cosmic wave still moving out from its origin point. When we look at the universe through the lens of time, we run into all sorts of paradoxes and complications. We ask, what happened before the Big Bang? A question that makes no sense if time itself began with the Big Bang. We struggle with the math of infinity at the center of a black hole. We get tangled in the complexities of quantum entanglement where particles seem to communicate faster than light, violating our time-based rules of cause and effect. But what if we took a bold step and removed time from our models altogether? Imagine cosmology without time as a fundamental ingredient. The Big Bang is no longer a moment time, but a transition of state, from a compressed ordered quantum system to an expanding complex one. A black hole singularity isn't an infinitely dense point in a frozen moment, but a stable state of matter where the forces of gravity and quantum mechanics are in perfect balance. Suddenly the infinities that plague our equations might just disappear. The math doesn't break, it gets cleaner, more elegant. The universe becomes a system of relationships, not a story on a timeline. This timeless perspective helps unify the very big and the very small. We no longer need to worry about how a quantum event can influence another instantly across vast distances. Without the constraint of time, there is no instantly, there is only connection. The universe becomes a single self-contained system where every part is intrinsically linked to every other part. The expansion we observe isn't something happening, but a fundamental property of the universe's current state, like the pressure of a gas in a container. It's a relationship between space and energy. By letting go of our human-centric notion of time, we might find that many of cosmology's deepest mysteries become easier to solve. The puzzle of quantum gravity, the nature of black holes, the origin of the universe, these might seem so difficult because we've been trying to fit them into a framework that doesn't belong to them. The universe's secret code may not be written in the language of clocks and calendars, it may be written in the timeless language of pure mathematics, of state and of transformation. To read it, we just need to change our perspective and see the cosmos not as a story that unfolds but as a magnificent eternal structure that simply